So today we're talking about SAT and SETH and all the lower bounds that it gives us, which are like in fine-grained complexity for polynomial time problems. The SETH is the most prolific conjecture that we have. So we will actually spend today and tomorrow talking about it, and we'll show a lot of lower bounds. And today is like kind of an introduction to this conjecture and to SAT and getting you comfortable with it. So I'm going to give two kind of talks now. The first one will be about ETH lower bounds. And then we will go, and the next one will be about SETH, the strong ETH. ETH lower bounds are not fine-grained enough for us. Like they don't give us interesting stuff for P, for polynomial time problems. But I think they're very good to know and to keep in mind, and I think they're very, very cool on their own. So ETH, as you just saw, it's like saying like, intuitively, it's just saying like 2 to the omega n is a lower bound for SAT. So it's not fine-grained because we don't know the constant here. It doesn't say what is the constant, and so on. SETH will talk about the constant. It will say that the constant is 2 for KSAT and so on. But what is cool, which I'll try to show you now, is that ETH is very powerful because it gives this kind of lower bound for pretty much every NP-complete problem that you know. Like all the famous NP-complete problems, you will get such lower bounds assuming ETH. So that's kind of satisfying. And so that's what I want to show you. And actually, the main tool that will allow this is this sparsification lemma. So I'm gonna tell you about it. It's also going to be useful for us when we talk about SETH, but not as useful. I mean, it's nice to have when you go to P. It gives some better parameters and stuff. It's not like extremely important most of the time. One thing that is important for, I think, is this exercise that Nick mentioned, which showing that SETH implies ETH, which is going to be on the exercise. There you were going to use the sparsification lemma to show this. So yeah, so I'll try to get you comfortable with this lemma and like how it's to use it and so on. I will not show the proof of this lemma. I will tell you a little bit about the proof. If you want to know the proof, you can talk to Karthik in the break. He wanted me to show the proof. So it's just going to take too much time. OK. So ETH lower bounds. Let's talk about specific problems, specific NP-hard problem, and try to get a lower bound for that problem. So dominating set is the problem I'm picking today. So dominating set is like, you have a graph and you want to find the fewest possible number of nodes that dominate the graph, meaning that they touch all the other nodes. So every node in the graph is either in the set or is a neighbor to someone in the set. If this is your graph, so like these nodes are not a dominating set because like they don't cover these nodes. Maybe if you add this node, then okay, now it's a dominating set. So you're trying to find the smallest possible dominating set. Yeah, just one of these NP-hard problems. So I'll define it as a decision problem. So you were given the graph and some parameter q, and the question is there a dominating set of size q? Again, the definition is that for every node, either it's every node in the graph, either it's in the set or there's a neighbor in the set. So there exists a U in the set. Okay. So as I said, it's an NP-hard problem. So let's look at the NP-hardness proof and see what it gives us in terms of the fine-grained complexity of the problem. So of course, like the NP-hardness proof just says that this is not in polynomial time. So there's some reduction from SETH to this problem. It's a polynomial reduction, and that's good. But then we make a stronger assumption. We say that SETH is not even in sub-exponential time. So what does it give us for dominating SETH? Does it give us the same lower bound or something weaker? So to kind of think about this question, let's look at this reduction. So do you remember the reduction from, or do you want to suggest a reduction from SETH to dominating SETH? Sorry?
Can we suggest from another problem, from independent SETH, it is very trivial?
Sure, but then it's going to be hard to see what ETH gives, because then we have to say, okay, what does ETH give about independent SETH, right? So no, let's start from SETH. So there's some reduction that's like, you take 3 SETH, and you go to dominating SETH. And right here we have some formula on n variables and m clauses. So we're going to create, so I'm going to give you like a hint on the reduction. The number of nodes will be 3 times n plus m. And the parameter will be n.
So you can make a vertex, so a vertex for each clause, and then the idea will be that whichever variable is 1, you remove that in the dominating set, and if you add an edge for that variable to the vertex for the clause, then it'll be dominated. And then, so yeah, I'm not sure where the 3n comes from. Like, can't you just have like a vertex for the variable as negation?
So you want, yeah, so it's okay. So these are the clauses, and you're trying to dominate them with the variables. So let's say this some clause here is like, some Cj is like x1 not, or xi, or xn not. So you want to connect this to some nodes that represent these variables. So you say, so what was the suggestion?
You could add a vertex for like xi and not xi.
Yeah.
But I'm not sure where the 3n comes from.
Yeah, so, okay, so this is x, this is trying to represent like xi, and this is trying to represent not xi. So then you want to connect it to like xi maybe, right? Like, so that if you want to set it to true, you choose this node. So then you cover this clause, and that's great. And I suppose you want to put an edge here, right? So that it's enough to choose one of them. Like you don't have to choose both of them, something. Okay. And maybe you're going to put an edge to the x1 not, because it appears negated. Yeah, I think that kind of works.
How do you make sure you don't pick both?
Yeah, so you might pick both. So let me just add a node, like a dummy node, just to I think it's going to be easier to analyze. Just like that's where the 3 is coming from. So I'm also going to add some dummy node here.
If you pick both, then you miss an edge. Because you can only pick n, right?
Yeah, so picking both is legal, but it's not going to be the minimum. So I'm adding this. So there's like these n gadgets. I have to pick one because of the dummy node. I know I have to pick one from, even without it, whatever. I have to pick one from, yeah, because of the dummy node. Otherwise, like if there wasn't a dummy node, I could have just picked something from here, and then that covers stuff, and that's going to be a mess. So I'm just going to put the dummy nodes. Now, the dummy node is not connected to anybody except for these two. So I have to pick one from, at least one from each. And the claim is that Same. So there exists a dominating set size q, which is n, if and only if it's satisfiable. Okay. Okay. Cool. So that's the reduction. It shows NP hardness. And so what is the blow up of the reduction? What do we get as a lower bound if we assume ETH? So the number of nodes depends not only on the number of variables, but also on the number of clauses, M. And what is M? So it's some polynomial. I guess we usually think of it as some polynomial. But what is the worst case? The worst case is that if every clause is there, then it would be n cubed. Because it's like n choose 3. So it's like at most. This is like a very. This is the maximum number of clauses you can make from 3 variables. It's O of n cubed. And then what this means is that we're going to get this kind of lower bound, 2 to the omega n to the 1/3 for dominating set. And let me do the proof, just because you probably are not used to thinking about this epsilon, this delta thing and stuff. I'm just going to do like a quick proof, like to prove that this 2 to the omega n to the 1/3 is a lower bound, and then we'll try to improve it to 2 to the omega n. So the theorem. So for the proof, we're going to assume that this is not a lower bound. So what it means is that for every delta, dominating set is in O of 2 to the delta times n to the 1/3. Okay. And we're going to use this plus that reduction to refute ETH. So what this means is that we want to get that for every delta prime, we want to show that 3 set is in right. Right, if we get this, that for every delta prime, we can show that SAT is in 2 to the delta, and then we refute ETH. And then, so we get this because, so to solve SAT, you just do the reduction. So given some formula, so we use the reduction. And you get a graph where the number of nodes is this 3n plus n choose 3. And this can be upper bounded very roughly by 11n cubed. And so we get that has running time So we get this running time because this is the number of nodes. So if we put it in this algorithm, we get like delta times this to the 1/3. And then this equals 2 to the delta prime n if we have chosen delta prime appropriately. Okay, so it's just some calculation to show you that, like, you know, what you expect happens. Any questions about this? Okay, but we want to get this lower bound, 2 to the omega n. So for dominating set, we don't have anything, we don't have that kind of bound for dominating set, n to the 1/3. That would be like amazing. So how do we get the higher lower bound here?
You try to reduce it, right?
Sorry?
You can try to reduce it and
Yes.
because like the n choose 3, there are a bunch of redundant moves like xi or xi or like negative xi. Those are but I don't know.
Yeah. I mean, you're right that the number of nodes here, like this upper bound, is pretty pessimistic. So you're saying like the maximum number of clauses in a formula is not going to be that; it's going to be smaller. But okay, maybe you're right. Like it's not this, 11 n cubed. Maybe it's n cubed over 10 or something. But it's still in the order of n cubed. I mean, you could have n cubed. Or fine, n squared, whatever. You could have like a lot of clauses in a formula, right? Mm-hmm. Yeah, I mean, if we could somehow sample a bunch of clauses and work with those only, then yeah, like I mean, you guys are right that the issue is the number of clauses here. Like if we could just reduce it, we would be happy. Sampling clauses, I don't know how it's going to work, right? Like it may be not satisfiable. You sample clauses, like you have fewer constraints, and suddenly it's satisfiable. So it's pretty dangerous. Yeah. But okay, but that's the point. Like if we could assume that the number of clauses was linear, not quadratic or cubic, then we would get the lower bound we want. We would get, instead of n to the 1/3, we would get n. And it turns out you can assume this. And the reason is this sparsification lemma. So this lemma says that SAT is just as hard if you assume that the number of clauses is linear. So let me write the lemma. Is this too small? It's fine. A little bit small. So I'm just going to delete the proof. I want more space. It's a long lemma. So I'm not done, but let me just say a few words about it. So it's one of these like reductions that have a huge blow up, but it's still useful. And that's kind of the thing to get used to when you do like fine-grained complexity. So we're talking about 2 to the n running time. And this reduction, it takes a formula and it produces a lot of formulas, this many, 2 to the epsilon n. But epsilon is like, we can choose it to be as small as possible. So just using this lemma, your running time is already exponential. But you can start thinking why like this is fine. It's like, at the end of the day, we just, there's some delta, we're trying to get 2 to the delta, and so we choose epsilon to be smaller than the delta and so on. But yeah. So I'm going to continue writing, but the point is, you take a formula, you get many, many formulas, but they're all sparse. They all have a linear number of clauses. So each of them is good. Okay, so that's the lemma. We take a formula, a CNF formula on some k. There's some k, like it's a k-sat thing. For us, it's enough to take k to be 3 for ETH. So just a 3-sat formula, and you specify some epsilon. You want you want number of formulas you get to be smaller than to the epsilon n, and you get some constant that depends on the 3 and the epsilon, such that each of these formulas that you're getting has the number of clauses be at most c times n. So you have the number of formulas is less than 2 to the epsilon n, and the number of clauses is constant.
How big is C?
C, I forgot, it's not written here. It's something like 1 over epsilon to the k over epsilon or something like this. Pretty big. And so let me just give you some idea of how you prove such a thing. It's not going to be a formal proof. There's some math behind it. But like, so the idea is you have your clauses. It's a dense formula. It has a lot of clauses. So you try to find, let's say, a variable that appears in many clauses. You find like the variable that appears in the largest number of clauses. Then you say, okay, either this variable is true or it's false. If it's true, then I can remove a lot of clauses because all of them are satisfied. So okay, you get one formula in which this variable is true and you've saved on the number of clauses a lot. Or it's false, and then you have this other formula in which you have just removed it from every clause where it didn't satisfy the clause, but the clause, it used to have k variables, now it has k minus 1. So maybe it used to have 3 variables. Now it has 2, so it's like much simpler. So you've made progress either way. And then you just continue. You do this recursively. Every time you pick like a variable, and then you split in 2. So you don't want to do this many times because let's say you do this epsilon n times, you are getting 2 to the epsilon n formulas, right? Because it's like exponential. But you can prove that as long as the formula is dense, there will be a variable that you can pick and will give you a lot of progress. And I think in the proof it's a little bit more subtle. You don't just pick clauses, you pick like sub-clauses, or you analyze sub-clauses. It's not, maybe you pick like a group of variables to make progress and so on. And the analysis is a bit like combinatorial, but yeah, that's how.
Everything here is deterministic.
It's a deterministic lemma, yeah. Okay, and now let's just see how this lemma with that reduction we get the 2 to the omega n lower bound for SETH, for dominating SETH. So it's just going to be another calculation like the one we did before now, but now it's going to be with this extra sparsification stuff. Okay, so we assume that dominating set doesn't have this lower bound, so for any delta prime we choose, no matter how small, we can solve dominating set in 2 to the delta prime times n. Then we use this to show that SAT can be solved in 2 to the delta for any delta. So let's fix some delta, and we want to get some algorithm for SAT. So we're given some formula. So we're going to choose epsilon for the sparsification. So epsilon will be delta over 2. So we had the formula, and now we have a lot of formulas. But they're all sparse. So the number of clauses is the C of 3 and epsilon times n. So we will set delta prime, the one for the dominating set algorithm, to be delta over 2 times 1 over 3 plus this C. Sorry?
You said delta prime equals delta prime.
Oh. Sorry? Oh, yeah. Yes. Thanks. Okay, so so now, so for each I, we reduce the formula to some graph where the number of vertices is this 3 times n plus mi, and we solve dominating set in this time. So then we just do the calculations. So for each I, the time we spent is 2 to the delta prime times n Then for all 2 to the delta over 2. Okay, I mean, it's just calculation. It's just like the point of the calculation is to show you that this like C and epsilon and so on, it can be worked out like to get the right thing. For the exercise for showing that SETH implies ETH, you have to do similar calculations basically. Okay. Okay, so now, right before we end this part, so I said like ETH is very cool. You know, it gives us all these lower bounds for all these problems. So, but the situation where you want to get more fine-grained is not very good for these exponential time problems. So next we'll talk about SETH to P, and we will get a lot of cool stuff. But as like leaving you with some kind of open question, it's like an open area kind of, is like figuring out the exact complexity of NP-hard problems, we know very little. So just like with 3-SAT, we have no idea what is the base of the exponent. For there's so many NP-hard problems where the base of the exponent is some weird constant, and we don't know if it's the right one or what's the limit and so on. So let me show you some examples. So dominating set, like it turns out you can do something non-trivial there. So for dominating set, you can do 1.4969 to the n. I'll try to find the reference and put it in the notes. I don't have it here, but it's kind of hard to find them because they improve with time a lot. So for maximum independent set, there's something like 1.119 to the n. For subset sum, it's actually a clean thing. It's 2 to the n over 3. 2 to the n over 2, sorry. For set cover, it's just 2 to the n. For 3 coloring, it's 1.33 to the n. If you talk about 10 coloring, it's 2 to the n. So 3 coloring is better than 2 to the n, 4 coloring also, 5 coloring also, but 6 no, and beyond it's not. Traveling salesman, 2 to the n. So it's nice at least that we have 2 to the omega n for everything. But we would have liked to have SETH lower bounds for these things, and we don't. Like, if you assume SETH, you don't get any lower bound for these problems. We mentioned one more. Max cut. The bound is 2 to the omega over 3 times n, which is like 1.7 something. So I mean, it wouldn't imply for everything because you can make like define a problem like artificially where like do padding, like the problem on you take square root n nodes and you solve a NP-hard problem. So the bound would be 2 to the square root n. And there are also natural problems where it's not the case. Like there's even under ETH there's even like n to the log n lower bounds for some problems that are not NP-hard. So it's not always 2 to the n. For these problems, I think it is. I mean, maybe I should have been more careful in checking, but for most problems, it is. And there's even a class of problems defined so that you have these like linear reductions from SAT to them. So these are problems where you have 2 to the omega n lower bounds under ETH.
Just to spell it out, why does it not work with sequence?
So right, so with SETH, okay, great question. So what goes wrong with SETH? So with SETH, I've deleted the definition, but the conjecture is about k growing. Like it's not talking about any fixed k. In fact, for any fixed k, we do have a better than 2 to the n algorithm. So then you really have to say k is growing, and then you go to this sparsification thing, and k is growing. So then c is growing. The number of so you still get like a linear density. The number of clauses is linear in number of variables, but the constant is growing. So if you want a 2 minus epsilon lower bound, like you have to go to some large k that's beyond that epsilon, and the number of clauses goes far beyond that. And then when you do these reductions, the number of nodes or whatever is always depends on the number of clauses. So the number of nodes is like a huge, becomes like a growing constant. It's never like a fixed constant. So then you don't get any lower bound under SETH. But you could make like an intermediate conjecture. You could say for 100 SAT, the complexity is 1.9. For fixed like 1.9 and fixed on 100, you would use this sparsification. You would get a fixed constant here, and then you would get a fixed lower bound like 1.0001 for these problems. You could do that, but.
Can you have like bigger function like n squared and cube?
Sorry?
Like 2 to the omega n squared or 2 to the omega n cube, how do you do it?
2 to the omega n squared lower bound for some problems.
If you have like n log n
Sorry.
you have like n log n permutation problems, can you have like bigger
Yeah.
like n squared and cube?
Not aware of any.
But it's possible, it's not like ruled out, right?
So there is something that is ruled out, yes. But it depends on how what is n. Yes, okay. If n is the input size, then I think you cannot go above n, like n squared or something. But for some graph problems, like the input size is n squared, really. So then maybe you can.
Yeah, but I guess it can be like that. But the input is like.
Oh.
So the input is always.
Right. No. So okay. So I think there's a general issue with going from two problems and showing a reduction where the complexity kind of grows. So you start with a 2 to the n lower bound, you want to get 2 to the n squared lower bound, or even like n squared, you want to go to n cubed, where n is the input size. Because then it's like you have to have a reduction that reduces the size of the input. That's the only way you could do it. Like to go from 2 to the n to 2 to the n squared, you have to somehow make a reduction to square root n size instance. And I mean, it's not like impossible. You could do it in artificial problems. You can do it and so on, but we don't have. Usually, it doesn't work. And
Well, like some of the permutation problems, some of isomorphism, you already do that.
sorry, for what?
Like some of isomorphism, you're able to do like I guess like n is not just the number of nodes, but like not the graph is in squares. You're kind of like
Yeah. Sometimes it looks like you did that, but it's not because of the graph size n squared.
I think I'm missing something fundamental. You're saying that assuming strong ETH doesn't give stronger lower bound. Why would that be the case?
So assuming strong ETH, you would have hoped to say like, let's say 2 to the n is a lower bound here, or 1.33 to the n, or even like 1.1 is a lower bound for these problems. You don't get that, and the reason is the reductions from SAT to these problems, like the one we saw with dominating set, the n will depend on the number of clauses. Now, what is the number of clauses? Okay, if it was n cubed like we had in the beginning, it's clearly too weak. Like you get 2 to the n 1. So you have to use sparsification. But then we use the sparsification. The number of clauses you get, okay, it's constant, but the constant depends on k. And SETH doesn't fix the k. It just says, yeah, for k, when k grows, so it's like it says, okay, when the number of clauses, it's like c at n, but c is growing. So you never get a fixed lower bound. the omega n. If you have any linear reduction from cell to that problem where the size of the input, like the number of nodes or whatever, depends on the number of clauses. Depends linearly on the number of clauses. Typically, you can what we had here with dominating set. It was like that, and typical NP hardness reductions do that. They have a linear blow up in the number of clauses, not the variables.
So what would happen if maybe SETH would pick another base problem as the hard?
Right. So people have looked at that. So I said there's nothing known. It's not true. There are some things that are known. For problems that I didn't write here, you have some lower bounds under SETH. For example, for subset sum, there is a lower bound that says. So for subset sum, there's two algorithms. There's this algorithm, and then also like the max number. If the numbers are from 1 to u, you can do this maybe times n or something. So there is a result that says that if you improve this to 1 minus epsilon, you refute SETH. So it's an example of an NP-hard problem with a tight lower bound under strong ETH. There's a couple others. And people have looked also at this conjecture that SETH cover requires 2 to the n, and have proven a few more, like for a Steiner tree, for example, you can get a tight lower bound. But there's very few of these examples. So even identifying one of them, I don't know which one, like SETH cover or coloring, and saying, yes, assuming that, I can get nice bounds for the others, that would be great. We don't have that. Notice that this is very hard because the reductions, let's say you start with this and you want to reduce to those and so on. The reduction, the blow up has to be like not even linear blow up is too much. You take n, you go to 10n. The lower bound, like the constant you get is like 1 over 10, smaller. So it has to be very, very fine grained.
Okay, this is a kind of a vague question, but can't you start the hypothesis like this for some problem in NP? There exists a specific constant delta which we think is the limit of all of the approach of any algorithm. Say that there is not there is no algorithm which does better than 2 with the delta n, and then start from that to lower bound. Is that really work this kind of?
Yeah, I mean this for SETH, right? We have this for. You start with SETH, and then for SETH cover, people have made that conjecture, and you can make it for other problems. But the issue is when you reduce it to other problems, you need reductions that don't increase the number of nodes, not even by a constant. Like from n to 2n, that's already making delta over 2. So it's very tricky.
When k is a variable in the specification, is it the number of clauses you get is dependent on k, or is it the size of the?
No, the number of clauses. That's the problem. It grows with k, like this function that I wrote there.
So does it t depend on k?
T depends on epsilon. So you have to choose epsilon to be small enough so that t is under control. Like t, epsilon is like, let's say 0.1 or something. So t is fine. It's like 2 to the 0.1 times n. T is just depending on epsilon. But then the size of the number of clauses, it grows with this epsilon, this 0.1 that you've chosen, and then also with k.
So to get this style of like exponential lower bound, are people using any other hardness conjectures, or is SETH sort of the most promising?
No, I mean, creating like a new type of conjecture sounds really cool, and maybe it's the right way. I don't know.
But
nothing that I'm aware of. No. Just SETH and SETH cover and stuff like that.
Do you have any SETH exponential lower bounds?
Sorry.
Do you have like any exponential lower bound that SETH?
Like 2 to the n lower bound? Yeah. There's a couple of them. There's a problem like hitting SETH, SETH splitting. There's problems like that. You can reduce SAT to them in a tight way, like n goes to n.
So it's just like you have a very tight reduction, you're not doing anything else, and you're just saying that it has to basically go to the solving SAT, and so it's like kind of that's the idea of it.
Yeah.
Or maybe to remember KSAT too. Does it matter or does it?
You have to reduce from KSAT, yes. So yeah, reduce from KSAT to these problems, but the K is fine. Like so that problem somehow eats it. Okay, so let's take a break, short break, and then we'll talk about the SETH to OV, which is like probably the most important reduction for P, because then OV is then like our intermediate problem. We reduce it to lots of prompts in P. And this reduction from SETH to OV is like the magic, where we go from an exponential lower bound to a quadratic lower bound. Yeah, I'm sure many of you have seen it, but